Okay, basically I'll start out looking at the sources of nutrients that feed these algae blooms, okay, and then the toxins they produce and what health effects they have on humans. Okay, the basic problem we've got, and this is a global issue here, and that we're trying to feed 7.5 billion people. That takes a lot of food, and that takes a lot of fertilizer. There's one number I want you to know, and that is the two major nutrients.
Yeah,
You prefer to use the mic? Okay.
Yeah, that'd be much better.
Okay, can you hear now? Okay, great. Okay. Okay, so the two nutrients that we need, the plants need the most of concerned here are nitrogen and phosphorus, and plants need these two nutrients in about a 16-to-1 ratio, and this will become important, 16 nitrogens to 1 phosphorus, okay? And so this is your fertilizer going to your crops, but fertilization usually is not 100% efficient, so some of it runs off rather than going into the plants. You have a lot of farm runoff into our various water bodies. These nutrients run downstream into your lakes, eventually the ocean, and so on. And they feed these algae blooms. The algae need exactly the same nutrients as the plants do on land. Okay? And again, roughly in that 16-to-1 ratio. So to the extent that you get this fertilizer runoff, you're going to get algal blooms. Okay? To the extent that the fertilizer does make it into the plants, we eat them, and eventually this ends up in sewage, and those nutrients don't disappear, they're in that sewage, and again, wherever you release that sewage, septic tanks or whatever, that's going to also generate algal blooms as well. Okay? So not surprisingly, look around the world, places where you get most of these harmful algal blooms are downstream of your major agricultural areas and your major urban areas, where you're generating most of the fertilizer and most of the sewage. Okay, this will be the most complicated slide probably. Okay, if you look in the ocean, okay, for reasons I won't go into here, you find nitrogen and phosphorus in about that 16-to-1 ratio. Like 99.9% of the ocean's got those two nutrients in that ratio. Okay? But particularly here in Florida, there's things that change that ratio, and I'll explain how this gets changed in a minute. But let's assume for a second, it seems to be kicking off and on. Okay. Basically, assume for a second that the runoff is in a 32-to-1 ratio rather than that 16-to-1. Okay? So the plants take it up in a 16-to-1 ratio, so what happens? You use up one of the phosphorus, you use up 16 of the nitrogens, you've got 16 nitrogens left over. So now, if you throw in, so this is now what we call a phosphorus-limited ecosystem. If you throw in more nitrogen, it doesn't do anything. The plants can't grow anymore because they've run out of phosphorus. If you throw in more phosphorus on the end, now you're going to generate more algae. Okay? On the other hand, if you start out with an 8-to-1 ratio or 16-to-2, the opposite now, and now the plants take it up in a 16-to-1 ratio, now what happens? You run out of nitrogen first, and you have excess phosphorus. So that's a nitrogen-limited ecosystem. And this has become very important, okay? And if you understand that concept, you're doing better than most of our politicians. Okay, so here's the map of South Florida, and my color scheme is going to be blue is low abundance of algae, and red is high abundance of algae, okay? So in the 1980s, a large bloom of blue-green algae developed right here in the north-central part of Florida Bay. And that's very strange. This is what got me going because I couldn't figure out what was causing this. I mean, think about this. You've got almost 3 million people living here. This is Miami here on the western side of Biscayne Bay. Yet you have relatively, it's not pristine, but it's close to it. It's actually relatively low abundance of algae compared to Florida Bay and compared to the west coast. And yet down here, you're in the middle of Everglades National Park. I mean, this whole area down here is Everglades National Park. It's protected. This was pristine Florida Bay. And then all of a sudden in the 1980s, you get this huge bloom of blue-green algae. It totally alters the ecosystem. It used to be crystal clear water. The bloom develops, the water becomes very turbid. Most of the seagrasses die. Total change of the fish population and everything else. So why is that? It doesn't follow that pattern of blooms being downstream of agricultural areas or urban areas. So that was the big puzzle. Okay, once I figured that out, Then I got interested in moving further north, see what's going on elsewhere. So I started looking at the red tide over here on the west coast, blooms and Lake Okeechobee. These red dots are just my sampling locations. Caloosahatchee River, St. Lucie, Lake Okeechobee, etc. Okay, so we're going to focus on Florida Bay first. This is just a close-up now of where that bloom of blue-green algae occurs right here in the north central part of Florida Bay. Okay, and the first thing is we're going to look at nutrients, and immediately you can see something's odd going on because you see high phosphorus in the western side of Florida Bay and high nitrogen in the eastern part of Florida Bay. Well, if it was fertilizer runoff or sewage, then those two nutrients should be in the same location. Okay? And they should be in roughly that 16:1 ratio. That's not what you see. So it tells us there's something else going on, and it's got to be at least two different sources. A different source for phosphorus and a different source for nitrogen. And it's just, these blue dots here indicate an N to P ratio, nitrogen phosphorus ratio, greater than that 16:1 ratio, which means you've got a phosphorus-limited ecosystem over here in the eastern part of Florida Bay, where you have a high nitrogen and low phosphorus. The red dots indicate a nitrogen phosphorus ratio less than that 16:1 ratio. And so now you have a nitrogen-limited ecosystem. Okay? That's the chemical data. There are some complications there, so we do what we call bioassays. Nutrient bioassays. We actually ask the algae, what are you limited by? And basically confirms the chemical data. Blue indicates, yep, this is a phosphorus-limited ecosystem here, and over here to the west is a nitrogen-limited ecosystem. Okay, so now we're going. So basically, the hypothesis here is you've got high phosphorus in the west, high nitrogen in the east, and where those two meet in the middle, turns out they meet. Let me back up. Actually, I forgot something. That when you shift from blue to red, that right there is roughly that 16:1 ratio. Okay, so where the high phosphorus in the west meets the high nitrogen in the east, where they meet in the middle, that's where you get the big algal bloom. Okay. So now the question is, where's that phosphorus coming from? And that is actually the toughest problem to figure out. Okay, it shouldn't be there. And the reason for that is the Florida Peninsula is really just a giant limestone calcium carbonate mountain sitting in the middle of the ocean. It's just sitting right above sea level there. Okay, and it's well known that calcium carbonate limestone chemically sucks up phosphorus. There's a chemical interaction that sucks the phosphorus out of the water. It's bound up in the limestone. Many studies have shown this, not only in Florida, but the Bahamas, elsewhere in the tropics, where you have limestone dominated. And so what's the source of so where do you get this phosphorus from? And it turns out, this took a long time to figure out, I was going through geological data, it turns out you go back to the Miocene many millions of years ago, there's an unusual oceanographic event occurred up here north of Florida, and I won't go into the details, but basically you generate a huge amount of what we call phosphorite deposits. And subsequent to that, there was an uplift of the Appalachian Mountains and eroded these phosphorite deposits down the Florida Peninsula. So today, you'll find these phosphorite deposits at the surface mostly right here east of Tampa Bay. And as you're all aware, they mine this stuff today. Okay? Just real quick. And they started mining this about 120 years ago for phosphate fertilizer. It's one of the largest mines in the world now for phosphate. Because you get these phosphate deposits only rarely. There's only a few locations around the world where you get these unusual phosphorite deposits. So just with pick and axe initially, and then the mines get larger and larger. They pretty much strip mined all of Polk County. You can see these by satellite here. You can see all those blue rectangles. That's the mining district there. Here's the Peace River, which drains there down to Charlotte Harbor. Oh. And of course, they have some accidents on occasion, sinkholes. Okay, and all the radioactive waste going down to the aquifer. Here's a aquifer scale. Okay. So that was my first hypothesis. Well, could that stuff be coming down the Peace River all the way down to the western Florida Bay? Well, so for a number of reasons I won't go into here, I concluded that was not the source of the phosphorus. Okay, and one of the pieces of evidence, and there's many different pieces, I'll just point out one here. If you go in Everglades National Park itself, there's a bunch of lakes and ponds, lagoons and so on that are not connected to the ocean. Over the eastern side, you see low phosphorus, and you move over to the western side, you see high phosphorus. So it can't be coming from the coastline. It can't be coming from the ocean. They're isolated. So where is it coming from? Okay, well, found some unpublished geological data. Turns out that while they're not at they're at the surface up here, but they continue underground all the way down into the southern part of Florida on the western side of the peninsula. And they hit the coastline in two places, the 10,000 Islands area here and the western Florida Bay down here. And they're about 50 feet below Florida Bay. Okay, so now then basically it matches very well. Where do you see high phosphorus? Western Florida Bay and the 10,000 Islands area. Okay, so now the question is, how do you get that phosphorus up from those deposits up to the surface? Okay, well, turns out that this limestone is relatively porous, and we have something called geothermal circulation. Okay, the core of the Earth is very hot, so if you drill down through the peninsula here, that water actually gets warmer and warmer. Okay, once you get below about 1,000 meters, 3,000 feet or so, it gets warmer. So what happens when you warm up water? It becomes lighter and it rises. You think of this like it's like a pot of boiling water, except it's very, very slow. And you're familiar with warm mineral springs, little salt springs, there's some offshore springs and so on. That's what's generating that. Okay, this geothermal circulation. So what we have here is geothermal, so the hypothesis is you have geothermal circulation coming up through those phosphorite deposits, bringing the phosphorus up to the surface. And that would explain that match. So we tested that hypothesis, and don't worry about the details, but basically we have a way of testing groundwater influx. We take advantage of the uranium-238, or the uranium-lead radioactive decay series that generates helium gas in groundwater. And basically, I'll just skip all the details, but basically these data here, we have excess helium in Florida Bay. It tells you you've got groundwater, you've got a significant amount of groundwater coming up into Florida Bay. So that basically explains how that phosphorus is coming up into Florida Bay from those phosphate deposits. So in fact, that phosphorus is naturally there. And then again, there's a lot of geological evidence that that's been there for millions of years. And again, basically, the bottom line here then is you've got those phosphate deposits all along the west coast. So the waters all along here are going to be relatively rich in phosphorus, and therefore a nitrogen phosphorus ratio less than 16:1, and therefore it's going to be a nitrogen limited ecosystem. Whereas on the eastern side of the peninsula, you don't have the phosphorite deposits. You've got limestone, which sucks up the phosphorus, and so you're going to tend to have a higher ratio of NP, and so it's going to tend to be a phosphorus limited ecosystem. I don't show the data, but Biscayne Bay is well known to be phosphorus limited, and eastern Florida Bay is phosphorus limited as well. Okay? And we can just continue right along the coastline. These red dots just indicate that, yeah, the entire coastline here is nitrogen limited. Okay? So it's going to be the nitrogen coming in from the land that's going to cause more balloons. Okay, so we can explain that phosphorus, but there's a problem there. That's been there for millions of years, but we didn't start getting the algal blooms in Florida Bay until like around 1981. Okay, so what changed? So we've only looked at half the story. What's the other half of the story? And that's the nitrogen. Where's that nitrogen coming from? Okay, well, first of all, it correlates well with yellow here is low salinity water, and the blue over here is saltier water. This is normal seawater here. This is fresher water, brackish water. That's fresh water coming in from the Everglades. Fresh water enters from the eastern side, not the western side. Okay. So here's eastern Florida Bay, where that nitrogen's coming in. So we're going to work our way back upstream through the Everglades up to Lake Okeechobee and what's called the Everglades agricultural area here, which is like 90% sugarcane. So we're doing transect from sugarcane fields down to eastern Florida Bay. Here's our sugarcane fields, here's Florida Bay down here. Here's phosphorus.